Hey. Yeah, can you please fill the thing for last time? I forgot to circulate it, the feedback form. Yeah, sorry, I messed up the month. Okay, so we start.
क्रेडिट वाले कुछ लोग आते हैं कम से
No, but it's time.
मैंने सबको जो हुआ था इंस्ट्रक्टर
No, we should start. I think it's okay. Anyway, it's just it'll take a few minutes to quickly recall what we were doing. Okay, so this was hybrid zero. Hybrid zero is the thing that we want to prove, and so what we wanted to do was to argue that this hybrid, so the output of this hybrid, right, is which is we're calling this z tilde actually, but yeah, maybe let's use the more recent notation. Yeah, so okay, this is the hybrid zero. Okay, and we want to show that, so we want to claim that hybrid zero, advantage in using hybrid zero is at most negligible. Okay, so we'll have to recall what advantage is. So advantage was advantage of hybrid I was simply defined as the trace distance with hybrid I acting on 0 and hybrid I on 1. Okay, and okay, so this is fine. So we wanted to show that this is negligible. So this is going to be the main thing we want to prove for hybrid 0. And so then to do this, we define two more hybrids. So let's see if we can write them out. Okay, so the first hybrid, yeah, so this is something I messed up last time. I mixed two hybrids. So yeah, so I need to first define hybrid 1 actually. So let's do that. So here you have the challenger, right? So the hybrid gets B. Challenger forwards this B, and wait, is the microphone actually on? Yeah, it is on. Good. Okay, you can hear me, right? It's all good. Okay, perfect. Okay, so the first thing in hybrid 1 was, I mean, you have it written, but I'm writing it again, so we can discuss. So you have EPR pairs on registers C1, A1, all the way to C lambda, A lambda, right? Okay, and C was defined to be C1 to C lambda. A was defined to be A1 to A lambda. And so that was the first part, the first step. The second step is it samples theta, 0, 1 to the lambda, and samples B prime, 0, 1, okay? And then x in 0, 1 lambda is the result of measuring C in basis theta. Okay, and then yeah, so this I'm going to call let's call this something. What do we call it? Let's call it 1 for now. Okay, so if B prime happens to match B XOR I for theta I equal to 0 xi, then you do 1, okay, and else you output perp. Okay, and okay, and at this step, once you know x, you apply z lambda, theta b prime a, and you get a response like at this point. So you get a response which is x prime a prime. Okay, and this was a lambda. Okay, so this is something we had discussed last time. And then I made one mistake by merging two hybrids. So this was hybrid 1. Hybrid 2, hybrid 2b is going to do the following. So hybrid 2b is exactly the same, except that this measurement is postponed to after that message has been sent and this has been received. Okay, so let me write it more clearly. Okay, so you do it at this point. Okay, this is hybrid 2. So far I've done nothing. Okay, so I just started writing because this you already know. This is what we wanted to prove, right? That regardless of whether you send 0 or 1, there should be no difference in the output of the hybrid. And remember, a prime is the residual state, all of the residual state. Yeah.
In that condition, you put in if xi is equal to xi prime. So for all I such that theta is 1. Is that different from writing if xi is xi prime for all? Like, they're not checking for if he's correct when theta is 0.
Yeah. So the I forgot the scheme now. So you were supposed to send. So some of them were supposed to be measured in the standard. Some were supposed to be measured in Hadamard. Yeah. So the thing is that I think the x prime that he's sending, the ones that are. So the point is that there are some which are in the plus and there are some which are in the minus basis, right? Like you have some states like this. It's some. Yeah. So these are the kind of states, right? So obviously, if you ask him to measure everything in Hadamard, you'll only check the plus minus ones, right? Because the other ones are random, so they won't match. Yeah. Because of this, right? Like this is the state you're sending. Yeah. It shouldn't have taken me this long to answer, but okay. Reading other things, I'm a little lost.
So it seems that you could also like check for theta equal to 0 and ask.
You could, but it won't work. The proof won't quite work because.
If we check for theta equals 0, as in if the adversary makes a measurement in the standard basis,
Yeah.
then the adversary will have the xi values for which theta is 0, right?
Yeah.
You
So
can flip it.
do b xor that and get the value of b.
Yeah, that should work, right?
It's a basis change. Like you can do a basis change on the whole system. Nothing will change, of course. Yeah.
But then the first step, you'll have to send b xor with.
I mean, then the hybrid 1 will also change accordingly.
Yeah, everything will change. Let's not change things. Let's. But yeah, if you change the basis entirely, yes, it will work. But yeah, there is some reason why you want to make a Hadamard measurement for the. Because you just want to make sure that whatever XOR you did over here, you get the adversary to measure everything in the basis orthogonal to that, orthogonal or whatever, conjugate to that. That's all the intuition is.
And in hybrid 2, the difference was you don't sample x, you measure. So what was the difference in hybrid 2 and hybrid 1?
Oh, you just delay when you're making the measurement. So in hybrid 1, you're making the measurement before you send z lambda applied to these inputs, and in hybrid 2, they're making the proof very clear. So they're making very small changes, which might even seem very trivial. So in hybrid 2, the only difference is that instead of measuring it before z lambda was sent, they're doing it after z lambda has been sent.
And z lambda was quantum state.
Z lambda was if you look at the definition, it was just saying that it's some sort of an encryption, right? So that is semantically not distinguishing the first input. That's what Z lambda was. All good? I'll close the door. Okay. So okay, good. So hybrid 2 is clear, right? Okay, very well.
So last time we said in hybrid 2.
Yeah, I messed up. I messed up. Yeah. That's what I was saying right towards the end, that I made a claim which I said was kind of straightforward, but that was not, because I mixed two hybrids. So hybrid 2 is this, and then there's hybrid 2 prime, which I will also write. So hybrid 2 prime. Yeah. Sorry about the confusion. And hybrid 2 prime of B does the following. So hybrid 2 prime of B is what we added last time, right? So instead of sending theta, you send 0 to the lambda. Okay, and that's when you ask me the indistinguishability. No, maybe not there, but okay. But yeah, so from the exercise, it should now be clear that I put on Discord that, you know, if you cannot distinguish 0 to the lambda from theta, it's essentially indistinguishable. Okay, yeah. Okay, very well. So let's continue with the proof. Okay, so we do recall the definition of advantage, so that is done. And recall also from the last lecture that we argued that advantage of hybrid 1 is at least half the advantage of hybrid 0. Okay.
What is the argument of hybrid I0 and hybrid I1?
Oh yeah, it's the bit B. Thank you. Yeah, it's the bit B, which we just forward to the challenger. Is that okay? Okay. So this is okay. Right. So this we remember, right? Because so we argued that with half probability it would be exactly the same as hybrid 0 in hybrid 1, right? With half probability, you will get exactly the same. The challenger will, the adversary will see exactly the same view as hybrid 0, and with the other probability, they just output perp, in which case you cannot distinguish. But at least in that half probability, you can distinguish with as much probability as you could distinguish hybrid 0. So this is fine, right? Okay, good. The next step is more fun. So the next step is also not too hard. Okay, so this is what I had messed up last time. As a consequence of having the definition of hybrid.
Why this was the case? So.
Oh yeah, here the point was that, you know, this hybrid 1, this B prime equals whenever B prime equals this object. Okay, it's not hard to check that whatever the adversary is seeing is exactly the same as what they would see in hybrid 0. Because what you've done is essentially you've purified the, you know, the preparation of this BB84 states, you've purified it, okay? And then you're just making some measurements on one part of the EPR, and depending on the answer, you would either have 0, 1 or plus minus, okay? And also, you were sending a random B prime, right? Instead of, here you're sending B XORed with the outcome of the encoding. Here you're just sending a random B prime, correct? So it would happen with half probability because you chose B prime randomly, that it would actually match this expression that you wanted, that it's B XORed with the encoding. Because B is random, so whichever, regardless of what bit was supposed to be there, with half probability you would match it. Okay. So therefore, with half probability, you're essentially, the adversary would see exactly what he was seeing with in hybrid 0, and so now. Therefore, you can at least with that, in that case, distinguish with at least as much probability as you could with adversary 0. Okay, so you get this one. The second one is the following. So now you're saying the adversary with hybrid 2 is identical to the adversary playing against. Oh my God, it's not adversary, it's advantage. Advantage. I'm so sorry. Maybe I should write ADVT. Otherwise, I'll keep calling it adversary. Advantage. Okay, good. So the advantage in hybrid 2 is the same as advantage in hybrid 1. Okay, so what did we do in number 2? Number 2, we just pushed this x to after receiving x prime. Okay, but clearly this makes no difference, right? Because it's a different register. This is just quantum mechanics. If you're a classical person, you might be annoyed by this, but quantumly we know we can always postpone the measure, even if it's entangled, as long as that first system is not being affected by the there's no communication depending on that first system. Even if it's entangled with the second system, you can always delay the measurement, and the correlations will be the same, right? So you won't see any difference. So this is nothing deep if you understand quantum well. Okay. Okay, and the reason is because register C is disjoint. So these kinds of reasoning is in brief just written as follows. So you just say because register C is disjoint. At least that's what they write in the paper. Is disjoint. So it's entangled but disjoint. Okay, so I don't know whether we need to do it from the registers. Registers A lambda acts on. Okay, so this part is fine. And now our goal is going to be the following. Okay, so we want to show that advantage of hybrid 2 is negligible. Okay. Okay. So, okay. Now to do that step, we need to add another hybrid. So let's do it. So now the story is send 0 to the n instead of theta. Okay, and so that's hybrid 2 prime, which we already defined, is use hybrid 2 prime. Okay, very well. Okay, and so now we introduce some notation for analyzing hybrid 2 prime. What is the notation? So we're going to say that okay, so consider C, the register C, okay, immediately after receiving okay, I never know whether it's IE or EI, okay, so receiving I'll probably spell randomly. From A lambda B. Okay, so you get x prime and a prime, right? And now register C was this, right? So now you're saying you know we're looking at that register immediately after receiving the result from the adversary, right? Okay, and then for any theta, okay, we set theta 0 to be I such that theta I is 0, okay, and theta 1 to be I such that theta I is 1. Okay, so that's just the definition. It's a bit unusual, but it's I guess useful nonetheless.
So all of this we are doing till now is just to formulate the security equation.
Yeah, we are trying to prove the security.
And not anything about the deletion.
What do you mean?
As in, like, we haven't formally proved that, like this, the one or the if condition actually ensures the deletion part, right?
So
No, but that's
hybrid 0.
yeah, that's hybrid 0. That's what we were trying to argue. Right? At the very beginning, we spent a lot of time on this, on saying why the definition is correct. That part you can only informally argue, right? You say this is what we want to prove, and you can say informally it captures what we want.
Okay.
But yeah, I don't think you can do much better than, because you have to start at some mathematical definition at some point. Yeah. So if you think of some weakness in the definition, that would be interesting, but it would have to be very subtle, because here the definition is just saying that, you know, whatever the state the adversary was holding, whatever register he was holding, after this is independent of B, right? So I don't know if you can make a strong, maybe there is a stronger notion, maybe, you know, like CPA, CCA, maybe there is some analog like that, I don't know. But yeah, I don't see it. That would certainly be very interesting to see if there is a stronger notion. Yeah, so we're assuming that definition, and we're trying to prove that the scheme that they've written can be achieved. It's true that they have kind of combined the scheme and the certified deletion definition into one thing, because normally you would not put like this part. This is actually the construction part. So they've merged the two things. So that I agree that there should probably have been a separate definition for any scheme to certify deletion, but okay, just makes things more involved.
So what is the meaning of considering or consider C? What is it?
Well, I haven't completed it. Consider means keep it in your mind, and then we're talking about that register. So I'm going to describe what I mean. So we're going to split register C into these two parts. So one part for theta 0, one part for theta 1.
So could you corner write the state, this CA state, the state on the register CA, and there was one more register. Just
Oh, CA is just, you know, like 0, 0, whatever, like say 0, 0 plus 1, 1 by root 2. This is on, you know, so every CI register has this form, sorry, CII. And then you just do a tensor over I.
yeah, that is I was thinking of Z lambda or something. So we did something with this state, right?
Oh, we did something with this state. Yeah, this is just, you know, trying to prepare, instead of sending 0, 1 plus minus, you're preparing EPR states and sending one part of that state, that's all. Okay. Yeah, we really should be able to complete the proof today, you guys. We're on the fourth lecture on certified deletion. It was like one of the small topics. Okay, good. So now continuing with the notation, the next thing we want to define is the following. So we have pi x prime theta, which is defined as h acting theta many times, theta 1 many times, x prime theta 1, x prime theta 1. So there's a projection, okay, and then there's a Hadamard acting on theta 1 again. Oh no, I've run out of space. Can you guys actually see or not? You can see? No? People behind can't see? Okay, I'll read it out for you, okay, and I'll increase the font in just a moment. C theta 1. Okay, so I've just written x theta 1 prime. So because x prime is a string, right? So it's a string, and you're looking at the you know, the indices for which theta was 0. Okay, so you write x on those indices and you apply Hadamard to all of them, and this you do on the registers, the sub-registers of C for which theta is 0. Okay, and then tensor, the same thing, except that the expression is a bit more interesting now. So this is where we're going to use the extractor that we had, theta 0, okay, such that delta y x prime theta 0 is half, and Hadamard on theta 0 y Hadamard on all of them, right? And this is on register C theta 0. Okay, where recall this is delta is relative. Oh, it's relative. I thought it was omega. Anyway, I may have used some wrong notation, but it's supposed to be the relative Hamming distance. Okay. So this is just a projector, and what is the projector saying? The projector is saying that wherever you had theta equals 1, okay, you assume you measure it in the Hadamard basis and got some answer, which is encoded in X, okay, and then the remaining part it is projecting on Y's, which are at most half distance from the output X, okay, and you're projecting on only such strings, okay. So if you look at the expression for the XOR extractor, you will see that there's similarity, because there we were measuring in the standard basis, right, and we were arguing that the other part, sorry, we were measuring in the Hadamard basis and we were arguing that the other part has at most half distance in terms of, so there is similarity, we'll use it. I'm just trying to tell you a little bit why this has been defined the way it has been defined.
So you apply Hadamard here also, like in the Y string.
Yeah, yeah. Yes.
So, so the expression is like it's ending on the top right corner and then starting another summation again, like the tensor product times sum over this whole thing.
Yeah. Yeah, it's a state on the register C, right? That's why I wrote this line. So it's the state on register C. It's a projector on register C. Yes. So the register C has been split into two parts, depending on whether theta was 0 or 1, and then on each part you're writing a different projector. Okay.
So you were trying some rationale behind this projector, but it will be clearer later on as well.
Yeah. It's just like some intuition. Okay, it will get clear as we go on. Yeah. So the intuition is just that, yeah, this has to do with the so intuition has to do with the XOR extractor. Okay. It will become clear. Let me not say too much now. It's fine. Okay. I'm going to erase. So I'm going to remove hybrid 0. Okay. So now we understand that what we want to prove is this, the last hybrid, which was that
Hybrid 2 prime.
yeah. So for now we are analyzing hybrid 2 prime. We'll have to show two things. One, we'll have to show that hybrid 2 prime bounds the advantage of hybrid 2. But right now we're just trying to show that hybrid 2 prime itself is negligible. Okay, so that last step also has to be done. Okay, so there are two things that need to be done. Okay. Okay. So let's make some more space here. Okay, so this is notation continued. So we defined the projector. Okay, now we're going to define the following. So probability pi x prime theta, output of hybrid 2 prime on B. Okay, so this is an object which we are going to define to be the probability that measuring this projector that we just defined, so pi x prime theta and identity minus pi x prime theta. So this is what we'll call accepts, and this is what we'll call reject. Okay, so these are labels. Okay, so the probability that you measure this on the output of hybrid 0, right, of results in accept on hybrid 0. Oh, sorry, hybrid 2 prime. Okay, good. So now the claim. So for any b in 0, 1, we want to argue that probability x prime theta prime, no, there's no theta prime, sorry, x prime theta on hybrid 2 prime b is at most negligible. Okay, that's what we want to prove. Yeah, and yeah, and then later we'll use this fact to argue. Yeah, maybe I can say a little bit at this point. So once we do the measurement, right? So once we know that, yeah, let me write it. Maybe it's too early. Let's just do the proof. Okay, so let's start with the proof. Okay, so suppose.
Before you do it,
Huh?
so why this is the probability of accept? I mean this pi x prime theta. So you wrote some projector.
Yeah, I'm just calling them. I'm just giving the labels. Oh, so hybrid 2 prime is the output, right? So okay, hybrid 2 prime formally is just the state that you get,
Yes.
right?
Yes.
So I'm just saying, so there's some density matrix,
Yes.
and this is some projector,
Yeah. Why,
and I'm just writing it as trace. Huh?
why this projector? That is what I'm asking. That why this projector gives you whatever we wanted.
Oh, you have no idea yet.
Oh.
It's a huge proof. Yeah, it'll take a while. We will prove little steps, and then they'll stitch together. So at the moment, we're just trying to show that the probability that you're going to see outcome accept is negligible. The intuition is that what we basically want to do is we want to use the XOR lemma, right? The XOR extractor. So we are trying to project it into a state which is similar to the state that we said we can assume initially for the XOR extractor lemma. So this is very similar because you see here it's saying that the distance is at most, like forget the Hadamard's for the moment. Okay, this is just saying that the distance between the y and the yeah, whatever relative distance is at most half, right?
So
In the XOR lemma, it was that the distance of all the y's was at least strictly greater than half, right?
yeah. So this will project at right.
Yeah. So you can use this projector to sort of argue that the state is close to what we want it, and then we can apply the XOR lemma and then argue independence and so on.
Wouldn't be the other way around, like right here it's at least half.
Yeah, we'll look at identity minus when we have to, yeah, because we want to say it's with negligible probability and so on. We'll see how it fits in. You're right, exactly. Okay, so we'll see. Like if I got something wrong at some point, we'll see. But in the paper when I read it, it seemed okay, so it should be fine. So okay, so now suppose, okay, can we start the proof? Any more questions before? Okay, so suppose hybrid 2 prime b is executed until a lambda outputs x prime and register a prime. Okay, so we are here. So you got x prime and a prime, and that's the point where we are at in the execution of the hybrid. Okay, so now there are a bunch of small notes. So the first one is that the register a prime may be entangled with C right. This is obvious because you sent C was initially already entangled with A, right? C and A were entangled. You sent A, and then that verse you could have done something, or even if it didn't do anything, could potentially still be entangled. So that's not a big thing to check. The second note is that so one can sample theta independent of A lambda's action, right? Okay, because we are in hybrid 2 prime, and in 2 prime we never send theta, we send 0 prime. Okay, so obviously you can sample this theta independent of A lambda. There's no correlation at all. Okay, and NB2, NB3 is the following, that the projector pi x prime theta is diagonal in the Hadamard basis. Yeah, that's trivial. Actually, they could have written it much more cleanly by just writing the Hadamards as, but okay, whatever. Okay, good. So now, suppose, right, x prime and theta are sampled as above. Okay, so x prime was sent by the adversary, right, and you stopped the execution, and theta you sampled independently. Okay, so you got these two. And suppose y is the result of measuring C in Hadamard. In the Hadamard basis, okay. So you have register C, you're going to measure, so you're going to measure all of register C in the Hadamard basis, and the outcome is Y. Okay. Then we'll have the following, right? So the probability that x prime theta acting on hybrid 2 prime.
X prime was sent by the adversary, right?
Yeah, yeah.
Then what we have sampled?
Sampled as above in the sense that, yeah, they're random variables. You can, are as above, you can remove that if you don't want to. No, actually, wait. Yeah, it's just theta that is sampled. X prime is what you get. So it's just like, there's a random, I'm thinking very abstractly, so I'm saying there's a random process and you're sampling things from the random process. But yeah, you can see R as above. Good. You're right. It's a bit unclear if I say sample. So this is better. Okay. So what was I saying? Yeah. So I was saying that the probability that you have this projector, according to that definition, right, you measure and you get the answer, is going to be the following. So it's x prime theta y. So x prime theta and y are the random variables that I specified here. And you have y theta 1 matches x prime theta 1, and distance of y theta 0 and x prime theta 0 is at most half. Yeah, okay. So why is that? So what is the projector saying, right? So the projector is saying that the projector is acting on register C, right? And we measured register C in the Hadamard basis, right? So we measured, so this Y is the result of measuring register C in the Hadamard basis. The projector is diagonal in the Hadamard basis, right? So then the constraint is just about the outputs, right? And the output here is, that you get x theta prime 1, this is y. So the condition is just that you got some value, right? So you got y as the answer. So the first part should match x prime, which is the for the projector, right? And whatever the remaining part, so on theta equal to theta 0 indices, whatever y you got should be at most at least half distance away. Okay, it's saying nothing at all. It's just saying that it's in the Hadamard basis.
I'm having hard time understanding. I don't know about the class because it feels like everybody's understanding. So I don't see the state. So hybrid 2 prime B state I don't see. You are giving a projector. Unless I see the state, I don't know what this probability is.
Yeah, you're right. Actually, I think maybe what I said was not fully correct. So I think he's thinking of okay, let's see. No, it's fine. It's fine. Yeah. Sorry. Ask your question again. I don't think I understood your question.
So if I know the hybrid 2 prime B state,
yes,
this is a state on some registers.
Yes.
Then I can think of what will this projector be doing to that state.
Right.
And then I can see this answer, but it's not very clear to me what is hybrid.
Why is it not clear? The definition is here. Because your the output. So you run this hybrid, right? Hybrid 2, and your output. I removed 1. Is that why it's not clear? I can write down 1.
I can say in node. So
yeah, 1 is just it's going to output this the A prime register, right?
So how does A prime look like?
Yeah, so the projector here was acting on register C. So maybe you're right, there is maybe some syntax mismatch. It could be. Let's see.
No, maybe it's clear.
No, you're right, because strictly speaking, the hybrid is only going to output register A prime, right?
Yes.
And here the projector is acting on register C. So
C stores the measurement outcomes, right?
Yeah, so
if everything is correct, the adversary might be whole. No, adversary cannot have C, otherwise.
No, the adversary doesn't have C. No. I think it's just a question of notation. So I think.
I think C was always with the challenger.
Yeah. So the thing is, when I write hybrid 2, I think, okay, maybe that's why they define the notation. So except on hybrid 2 prime B, I think maybe the right way to think about it, which is like overloading the notation, is that you look at the challenger and then you make a measurement on challenger's register C. So it's not strictly the output state. So that's a good point. What I said was wrong, right? So I said whatever the output state is, you're measuring it on this, but the output state is register A prime. It's not register C. So it syntactically doesn't make sense. Here, what they're thinking of this is the process, the entire process, hybrid 2 prime, and they're saying that in that process, C gets, it's not, C is basically disjoint, right? So you can measure C whenever you want. So they're just saying in this hybrid 2 prime, register C is what you measure, and you get certain answer. You're right, yeah.
Yeah, so I'm thinking that can I write this full register at this level?
You can write it at any point you want. Because register C is just one half of the EPR, right? So you can write it.
We had EPR pairs and then we instead to sample theta, B prime and so on.
Yeah.
And then adversary does something.
Yeah, so you have to include the actions of the adversary. So it will change some, it'll affect register A because C was never sent to the adversary.
So A was with the.
Yeah, so A is with the adversary. The adversary can apply some operation, right, and return this answer. So it can return X prime and A prime.
And I think, you said that Z lambda is operation.
Yeah, Z lambda is an operation. Yeah.
That is an adversary. Adversary register.
No, Z lambda is sort of like the encryption scheme because we are doing it more abstractly. You can think of this as some encryption scheme, which is fixed.
So encryption scheme on the adversary register. What is it?
No, A prime is what the adversary will send you back.
Yeah,
A and B prime are, so this is, so one of the registers is so this is A is what will be used to do certified deletion, right? So you remember how we had you have some string which is XORed and then you had a state, quantum state that had to be, so if the adversary wanted to delete it, he had to measure the quantum state in some basis. So that's what this part is.
Yeah, so this is like some steps.
So yeah, so this is just the scheme itself. You're saying that there is some scheme and it sends this.
This
Yeah. So just a sec. Let me finish what
Yeah,
was.
so yeah, so now
Unless you're clarifying something, I don't know. Ah, okay.
okay, so I can see the state, then maybe you can argue later.
Yeah, you can. You will not be able to write the state explicitly because we are reasoning abstractly, right? We are saying we don't know what the action of A lambda is.
Right, so argument I should remember the arguments, all of them together.
Yeah. But here, yeah, your point was correct that this is just a measurement on register C of the hybrids. So that is something I got wrong. So thank you for spotting that. And then once you have that register C, we are just saying what is the probability. So can you actually write it down more clearly? And this is how you write it. So remember, x prime is coming from the adversary, right? So this x prime sent by the adversary, and y is the result of measuring register C. And now you're looking at the correlation between y and x prime. So you're putting some conditions on them. Okay, good. Yeah.
This register A is where it's like sent to the adversary.
Yeah. You also had a question.
Yeah, I'm actually kind of still stuck there in the projector.
Oh shoot.
The first part is when C, like the indices where your theta is equal to 0, right?
Theta is 1.
Theta is 1.
Theta is 1, and
Yeah.
the second part is when theta is 0.
Yeah.
And then later you're comparing y theta 1
Uh-huh.
x prime theta 1.
Uh-huh. Yeah, I'm looking at the corresponding registers, right? So I is the index. Oh shoot, I erased the. So recall the notation theta 0 was set of indices for which theta I is.
0.
Yeah, so I don't like the notation because it's using theta 0 also here and also here potentially, which is a bit
Those
confusing.
y's are different.
So they are
No, it's like this. Like think of it this way, right? So you have these kinds of states, right? 0, 0, 1, 1 on AI, CI, right? No, sorry, CI. What was it?
CI plus.
Oh yeah, CA. It doesn't matter. Yeah, it's fine. Yeah. As long as I'm labeling them, it's fine, right? So this is just saying what? It's just saying that intuitively what we are saying is that if you measured A in Hadamard, then I also want to measure C in Hadamard, something like that.
Yeah,
So you'll have a set of indices for which theta 0 corresponds to theta I equal to 0. So I can write that on register A, I can write that on register C. So when I write y sub theta 0, I'm thinking you are taking C, right? And you're looking at the subset which was measured in 0, in standard or Hadamard.
So could you repeat your question again so that RMS?
Yeah, like I just got confused between. So there's those y's over there in the projector.
Yes.
So
There
I'm
are two
wondering-
parts actually, right? So
Yeah,
there's
so this is in the second part where
Yeah.
theta is 0.
Yeah.
So
here also you have two parts. So there is and between there, right? In this expression of probability, you have y theta 1 equal to x prime theta 1 and the relative having distance is greater than half.
Yeah.
okay, I got it. So this is.
Oh, you were concerned about the and. Oh, yeah. This is.
No, so this is also in that part.
Yes.
I got it.
Yeah. Yeah, there are two parts, right? Like, so y is like a big string. There's like theta equal to 0 part, theta equal to 1 part. And yeah, if it helps, you can just imagine that, somehow you chose theta to be like this, right? Like it was 1, 1, 1, 0, 0, 0, 0. So you're arguing about this part and arguing about this part separately, that's all. It's just that you don't have to choose them in the order, so it's hard to write register, so they have to put some notation. Yeah. Okay. Is it okay for everyone? I'm sorry, okay, this is just like notation. We're not really doing anything interesting yet. But it's good to clarify the notation because otherwise nothing will make sense.
Some people get lost here, then
Yeah, then nothing will make sense. Yeah. No, it's good, it's good. It's clear, right, to everyone? Yeah? No? Okay. Okay. Let me know, okay, if something is not clear, we can... okay, good. Subclaim. In trying to prove the claim. And this we will not prove. Okay. So I'm going to write down the reference, and I don't remember what BNF stand for, so you'll have to look at the paper. B might be Brandau, actually, I don't remember. But yeah, so what is the claim? Okay, so since I don't remember the thing. So the claim is that for any fixed x prime, this probability can be bounded using standard Hofting. Inequalities as 4 times e to the minus lambda half square by 32 whatever, which is a negligible function in lambda. Okay. So here what you're saying is you have this so these random variables, right? Yeah. So okay, so y is the result of measuring some register, right? Which is like essentially a fully random variable. And then you're asking what is the probability that for some whichever x you can choose whichever x prime you want. What is the probability that this expression will be true? So that half of them you actually match the outcomes of the Hadamard, and the others are farther than half in Hamming distance. Okay. Of course, it's like saying if you measure all of them in the Hadamard, you will get the right answer with probability 1. So he's asked, basically they're trying to argue, it's just an exercise in like sort of independent coin flips and these kinds of things. I also haven't looked at the proof, but I'm believing it for now. But that's the intuition, that you have to, if you're measuring this predicate and everything matches in the Hadamard, then the others should also be unpredictable somehow. It shouldn't be that you can, in the same spirit as the XOR.
So Hofting actually requires the average, like Hofting just tells you that the expected average and expectation values, they are bounded by some quantity. So here we must compute the average value of average value of random variable y probably, which will depend on other things.
Yeah, maybe this could be a good exercise. It's I think good to check. I'll also look into this. I didn't put in the assignment because I myself don't know how to solve it. So once I figure it out, I guess I'll put it in.
The trouble is that other paper will have the same notation or not, because
no, that's good, yeah. Because we'll see what is meant. But I think it's maybe like a very basic fact that it is good to sort of know in quant. Okay. Okay, so this is fine, and yeah, so the intuition that I've written is that it's basically saying that if you hold a purification of C, okay, you cannot send me a string such that when I measure C in the Hadamard on a random subset C theta 1, it matches, but on the rest it differs on at least half the places, something like this. So because you're given C, right, you're going to randomly pick half of them because it was independent, right? So the statement is I randomly pick half of them. It cannot be that they match on those whichever random subset I picked, and on the rest all the y's are far away. So this cannot happen. That's kind of the statement. Okay. Okay, good. So now we're on.
Yeah, this next one. The x prime was random. Sorry, y is.
Yeah, it's just formalizing the same intuition.
Which one?
Yeah, so y is the result of measuring everything in the Hadamard basis, right? So this is intuitively saying that.
Okay, so y is random and x prime was given by the adversary. So if you put some condition on it, it will be unlikely.
Yeah. So because the adversary doesn't know which one I want him to measure in the Hadamard and which ones I don't. So it cannot be that he does both. Like, so it's kind of really formalizing the initial intuition we had that you cannot. Without knowing which basis to measure, you cannot produce the correct answer.
Doesn't that render? So if my string length is very small, so
that's why you have lambda, right? The security parameter. So it's negligible only in lambda. So if you have enough strings, it will become exponentially harder for you to get everything right. Yeah. Okay. Good. So let's move on. I'm trying to decide what I should remove now. Okay, maybe I'll keep the projector. Let's remove this part. Okay, so this claim is done. I'll keep the claim because okay, good. So here's a small notation in addition to what we were doing. Yeah, okay, so the notation here is that we'll use essentially the same notation when we are referring to the second hybrid instead of hybrid 2 prime. Okay, so that's just, so nothing very big here. Okay, and now the next claim that we want to show here is claim 3.4, which is that it was the same statement except for hybrid 2 now. So for any b in 0 1, probability of pi x prime theta hybrid 2 b is negligible. Okay, so the proof is actually fairly standard because we are going to use semantic security, right? Because what is the difference between 2 and 2 prime? The difference is that you replace theta with 0 to the lambda, right? So what that means is that if you could somehow have this operation output some value which is not negligible, right?
Hybrid 2 prime.
Then yeah, so you know if in hybrid 2 this was not negligible, there was some something you could detect, then you could use this projector, because this projector is efficient, right? Like in the sense that you know the procedure to produce the output. So you can run that procedure and construct an efficient distinguisher between hybrid 2 and hybrid 2 prime. Sorry, between encryptions of 0 and theta. Okay. So this will follow from semantic security. I'll leave it as an exercise. I'll put it in the assignment because we need to finish the proof, and this part is not all that. Okay, so this follows from semantic security. Okay, and the crucial bit here, and this is kind of the important, the technique that they used here was that this pi is an efficient, so they show that this measurement that you're doing, basically just making Hadamard measurements, right? You're not doing anything very complicated. So this projector, you can realize, given x prime, you can construct the projector efficiently. And that is important because now you're using computational efficiency, right? You're using the fact that it's semantically secure but under computational assumptions. Okay, so 3.4 is going to follow from that. Ooh, we might actually finish the proof. Okay. So we have all the pieces now. If you have time, I'll show you the proof of this as well. But let's move on.
Actually, single depth circuit, right? Because this is
Uttam and his depth. Yes.
all Hadamard, right?
Yeah, probably. And you also have to produce all the x's and control them a bit on x prime.
X prime is given to you, right?
Yeah, I mean, you may have to control or something, but I don't know. I haven't thought about the depth, but yeah, it doesn't look like it should be very deep though. Yeah. Okay, good.
There should be some control using x, right? To find whether theta is same.
Yeah.
Theta doesn't depend on x. Theta depends on theta. This is also given to you.
Yeah. Okay, so now we have all the pieces. We have the pieces. For the full proof, or to complete the proof, whatever. Okay. So now the final claim. Actually, no. Okay, yeah. So one thing maybe which I should mention, which I did not mention, was that I remember I was trying to argue that that the advantage in hybrid 2 and hybrid 2 prime would be the same, right? This is how I was initially trying to argue. But the point is that we didn't really use that, strictly speaking. The only thing that we used was that this projector on hybrid 2 and this projector on hybrid 2 prime, they are essentially going to be negligible. Okay, so we didn't really say that the advantages are going to be the same. We just argued that we used hybrid 2 prime to argue that the projector on hybrid 2 will also be negligible. That's all we used. Okay, so it's a little bit more subtle than just showing all the hybrids are equivalent. And the reason is precisely that one of them is computationally secure. So you could not, because you need statistical security in the end, right? So if one of your equalities in the sequence was computational, then obviously everything becomes computational. So it's not good. So okay, so that was just the one thing I wanted to mention. So now we can prove the claim. The claim was that advantage of hybrid 2 is negligible. Okay. And the remaining ones were the same as hybrid 2, right? So this we saw. I mean, they were negligible if hybrid 2 was negligible. Okay, so what's the proof? Okay. So first note that for any b in 0, 1, the global state of hybrid 2 b immediately after a lambda outputs x prime. Okay, so we're looking at, like what you were saying, the global state that this hybrid 2 produces immediately after a lambda has sent x prime. Okay, x prime and a, but we don't write that, is within negligible distance of a state which we'll call tau ideal C a prime in the image of identity minus pi x prime theta. Okay, is that clear? So what we are saying is that the state right after here, okay, so this state is going to be some tau, right, on register C and A prime. So A prime was sent by the adversary, C prime was C was what you were holding as the challenger, and we just argued, right, that being in the image of pi x prime is negligible, right? That's what this claim is saying here, this one, right? So you could not possibly be in the image of this because the probability that you're getting that outcome is 0, essentially. So therefore you necessarily have to be in the image.
In the support of this project, right? Image is correct use. So
Yeah, you can write support. Maybe I messed up, but
you mean that the space is spanned by this projector, this tau C A prime will be in that space?
yeah, you can say support if you want.
It means that if I apply I minus pi x prime theta on this state, you will get non-zero answer.
Yeah, it's basically in this space. That's it. It will not be. So if you apply the projector on this, you'll get the same thing, essentially.
Same thing.
Yeah, it's just, you know, there's like spaces spanned by projectors, right? So this is pi x, this is identity minus pi x. So you're in this space, that's all. Yeah. Yeah. I think image was also fine because you take any register X acting on the anyway, whatever, doesn't matter. But that should also be okay because it's just X acting on pi, right? This would be the
This to be non-zero.
wait. So this is over all X, right? This is the image of X, correct? No, image of pi. Sorry. Which is also the same thing, right? Like it's. Anyway, it doesn't matter. But you understand what I'm saying? Yeah, it's all vectors. But yeah, maybe I miswrote it. It could be. Oh, okay, good. Okay, so yeah, so why? So formally, why this holds is because of claim 3.4, right? And the gentle measurement lemma. So because this is just saying that there's a certain probability of getting the output. So this was saying trace of this thing is going to be negligible. But then you need the gentle measurement lemma to say that if the disturbance is small, then the states are also close and so on. Okay, so one can prove this, that the trace distance is small. Okay, so that was one step. What do I want to remove? Okay, let's remove this now. Okay. Okay, and at the next step, the challenger in hybrid 2 checks whether the Hadamard measurement of C theta 1 of tau C A prime matches X theta. Okay. So we are dividing the challenge in 2 steps. So this is, we got stopped just after it received this X prime A prime. Okay. And now we're going to measure, continue with what the execution says. So at the next step, the challenger measures in hybrid 2, right? Checks whether Hadamard measurement of C theta 1 of tau C A prime ideal matches X prime theta 1, right? So that's fine. Okay. Is this okay? Okay, so now there are 2 possibilities. Okay, I'm going to erase this now. I think we kind of made use of it already. So there are 2 possibilities. The first is if X prime theta 1 doesn't match, the output is perp irrespective of P, right?
The adversary is trying to cheat.
Yeah, but it's matching B prime, right?
No. It's just producing, it's checking if the deletion certificate is, so this is 1. I should probably, let me write 1 because, if theta is equal to theta prime, let's write it down here.
Okay, you are checking if adversary has actually measured.
Yeah. So if xi equals xi prime for all I such that theta is 1, you output A prime, right? Else you output perp. Okay. So now the way this is arguing is it's saying that if it were the case, right, that x theta 1 doesn't match, right, then this would, you know, in our new notation it's just x theta 1 equals x theta 1 prime, right. Okay, so obviously if this would fail, and you would certainly output a bot irrespective of what b was. Okay, so that's the first case. The second case is if x prime theta 1 does match, okay, then the state on c theta 0 is only supported on span of h theta 0 y such that the distance between y and x0 prime is at most half. Okay, and that is because of the tau ideal. So this is because of, let's say, star. Okay. So if it does match, right, then you're guaranteed that where did I write that? Yeah, so what you're guaranteed is that, so because your state is this, right,
So
is in the orthogonal space,
yes.
so it could not possibly on 0, it could not possibly have had any y which was
Yes.
more than half, right. So it necessarily has to have y's with x prime 0 being strictly half distance away, right.
So argument you are following, right? So if adversary did measure, then you claim from general measurement lemma that the state should be tau c a prime, right? And that state is supported on the space identity minus pi. So if anything is supported on identity pi x prime theta, then it will not lie in relative having distance greater than half.
Yes, so the theta 0 part will not lie.
Yeah, you are not worried about theta 1.
Yeah, yeah.
If the adversary measures,
Mm-hmm.
what?
Sorry, I couldn't understand the question. Say it again.
What is the adversary measure?
What does the adversary measure? The adversary is just sending x prime and a prime. Where's the adversary measuring?
Yeah, the x prime is obtained after.
So you mean when the challenger measures?
Did I write adversary measures?
No, I was saying this only because the adversary is sending x prime, so he could have either measured or he could have just sent like as it is.
Yeah, you just assume that without loss of generality, you assume x prime. There's like, that's why in the beginning we said, you know, you pass it as getting some classical and some quantum state. Okay, So if
I mean, cheating adversary would mean that, right? Cheating adversary will mean that he ignores the protocol and sends some random.
yeah, that's without loss of generality. You add a measurement in the x prime part. Yeah, that's not a problem. It's equivalent to whether the adversary measures and sends or you measure for the adversary. It doesn't matter. Yeah. You're just getting a classical variable. Yeah. Okay. So
So is there a problem for you? You look like.
is it good? Is it good for everyone? Yeah. Okay.
Over there, what would be like greater than equal to the delta?
Why? Okay. But look at claim 3.5.
Oh, like identity minus that.
Yeah. Okay. Okay, so we have this condition. Okay, so then it says okay, let me write it, but I don't want to write it. Okay, so this is continued from there. So now the challenger then measures these qubits in the computational basis. Okay, so by these qubits I mean the one on c theta 0, right? To obtain xi. Okay. And checks, right, if I is theta equal to 0, xi is not equal to b prime x or b, then outputs a bot, otherwise outputs a, right? Okay. And now the note, shoot, we're out of time, aren't we? Okay.
7 minutes.
No, it's still. Oh, do I have until 30? I have. Oh, nice. Okay. Oh yeah, we start 5 minutes late. Okay, good.
No, the timing is 10:05 of your class.
Yeah, that's what we start 5 minutes after 10, but we end at 11:30.
Yes.
Not early. I was thinking it's also 11:25. That's why I was getting a bit worried. Okay, good. So we'll be able to at least complete the argument. So the first notice that this is the only step, right, that depends on B. Right, because so far nothing depended on B, right? The entire analysis was independent of B, so that's good. And from theorem 2.2, which is the XOR extractor, so from theorem 2.2, which we'll explain in just a moment, okay, it follows that this I theta I0 xi is I've really run out of space. Okay, let's continue here. Is uniform and independent of A prime. Okay. Thus, the output of the challenger is the same for b equal to 0 and b equal to 1. Okay. So it's that last implication that I still have to prove to you. But assuming that, you know, your state was of this form, right? We are really very close to proving what we wanted, because remember the XOR lemma was saying that except for the Hadamard, right, and suppose x0 prime was 0, right, then it's exactly the statement of the XOR lemma, right, because the XOR lemma said that if I had some state of this form, right, it was like some phi y, and then I had a sum over y, and my y was at most half in whatever omega, right, and then I measured this in Hadamard, right, then I'll get a string which I XOR, and then that is independent of whatever the adversary was holding, correct? So we're almost there, right, except this is in the Hadamard basis, okay, and it's offset by some x, okay, and it's not too hard to show that you can essentially apply the lemma by one small change of basis and making a measurement. Okay, I leave that last part also as an exercise, but we essentially have the same form, okay. And the crucial thing with that lemma was that it gets you completely independent of whatever the adversary was holding. So, and in this case that was register A, right, because A could have potentially lots of things. So that gives you certified deletion. Okay. Still have 2 minutes.
What about tutorials? So will you be taking tutorials?
Yeah, I don't know how this stuff works. I don't. I thought they would.
Yeah, because this thing still is heavy for me, so I would probably read and then.
Right.
So I don't know what others feel.
Yeah. Maybe we could have office hours. I don't know how tutorials work. Are you supposed to?
That depends on faculty. You can teach some other things which you are not able to cover in the class, or you might augment the things.
Okay.
I was just asking if you will have it.
No, I don't know how to do these things. They just said you have 2 lectures to teach. So I'm teaching 2 lectures. I didn't know how the.
Yeah, then the people who are crediting might decide what they want, because you will get extra time also, right, for tutorial, so that you can use in any way you want.
Oh wow. Okay.
Right?
Yeah, that's like one more lecture.
Oh, so then we could have gone so much faster.
Yes.
What the hell? Oh, okay.
Yeah, you use that 1 hour either to clarify or.
Can I get backlogs in tutorials?
No.
Oh man. Okay. Huh. Okay. So yeah. Oh, don't forget to fill the feedback, please. Have you circulated it? Maybe also send it to others.
So what will be next? So this proof is done completely.
Yeah, there's like that little part which I leave as an exercise, and people can sort it out.
So this is
Yeah.
And that is what you will cover in this topic of deletion, certified deletion.
Yeah. We already spent 4 lectures, but I think it's pretty good. What do people think? Was it clear? Did you understand? Yeah? It's too easy or?
Not too easy to understand.
Okay. That's good.
So what will be next?
Yes, I was thinking of doing unclonable encryption next, but that is much more involved, so I'm not sure if we'll see.
But when we are doing quantum cryptography, it will be involved.
Yeah, like there's also verification, there's also FHE. Those are like relatively simpler because people have already done the hard work of simplifying them. So these are like directly research papers. So
does it? Does it help if we read first FHE and then unclonable, or it doesn't matter?
I think they're different flavors.
Yeah, but language you get more comfortable. That more time is spent.
Yeah. It's too unclonable. It's good to do hard things, then later we can do easy things.
That is up to you, because this unclonable and clonable encryption people are doing recently in research, right?
Yes, it's better. No, you'll be at the cutting edge, and there's lots of open problems. Like in like verification and FHE are pretty much sorted. So those are like things you should know, but.
No. Shreyas is doing research on verification.
Yeah, like I mean BQP, like yeah, of course. Those are like central open questions, of course. Yeah. Yeah, I think if you solve that, you probably just get a faculty position right away, something like that. I think it's those are. Yeah, there's no reason why not. It's like Urmila solved verification, and FHE she got a position at Caltech. So.